Good job not forgetting to record.
And my memory doesn't suck today, but that's just because I drank a lot of coffee. Because papers. Okay, so we will start talking about somewhat more concrete uses of the derivative. I dislike the the usual title for this chapter in like AP Calculus is Applications of the Derivative. I don't like that title so much because we're really talking about the significance of the derivative. So we're going to not necessarily apply it to concrete, say, physical or engineering problems, which, to my mind, the words application of derivative seems to suggest. When I started studying this chapter in AP Calc in high school, I was like, oh, applications. I thought it was going to be to science, but this is really the significance of the derivative we're going to discuss. So I'll start by trying to give like a bird's eye view, just broad brush idea of what I mean by significance of the derivative, the sort of things we'll be talking about. And then we'll dive in with some specific examples. We'll start with extrema and optimization, and then prove first Raleigh's theorem as a lemma, but then really use that to get to the mean value theorem, which is a very important result. It's kind of like the derivative version of the intermediate value theorem, the IVT we proved when we were doing chapter 2. Okay, so first the bird's eye view. This is going to be no proofs, just pictures to help acclimate yourself to the sort of things we're going to be talking about. So the overarching goal here in chapter 4 is to analyze graphs of functions or understand the properties of graphs of functions using this tool, the derivative that we've just developed. Since now we've spent a lot of time taking derivatives, doing differentiation, we should see why this is useful in analyzing functions. So one obvious thing that you might have noticed is that if a function is differentiable everywhere, so say it's C1, so it's smooth, since the derivative gives you the slope of the tangent line, you might have conjectured or guessed just by looking at a graph that you can tell a function is increasing when its derivative is positive, right? So f prime is positive in this region means that f is in fact strictly increasing. So whenever you go to the right on the x-axis, the function output is also going to go upwards along the y-axis. Similarly, if the derivative is negative here, f prime is less than 0, so the function is strictly decreasing on this interval, and it's back to increasing here. So you might have guessed this just by kind of intuition of drawing graphs and thinking about the geometry of the tangent lines. Of course, this is not a proof. We need to prove, actually, that the sign of the derivative tells you whether a function is strictly increasing. That's going to be one of the major things we prove in this chapter. But perhaps already you would have guessed that just by looking at pictures. Good. Thoughts or questions on this?
I have none.
Good. All right. Not super complicated, but okay. So something we'll discuss today is so-called extremization. Extremization means finding either a maximum or a minimum. So you use the word extremum when you want to be non-specific about whether it's a maximum or a minimum. And this is probably the most common application of calculus outside of mathematics to other fields like economics or finance, for instance, is using calculus to find where a function is larger or smaller than a bunch of other nearby values. And again, intuitively, we're not proving anything here, but you might have guessed that unless a function has some very jumpy, discontinuous, or non-differentiable behavior, if the function is again C1 or smooth, you might have guessed that anywhere the function has, say, a local maximum, which means it's larger than its values at all nearby points, but maybe not larger than all other values on the entire line. So at a local maximum, you would think, well, the derivative should be 0, because if you're at the top of a mountain, your tangent line is flat. If you're, again, in the bottom of a valley at a local minimum, your tangent line is again flat. And then here's an example of a maximum which is both local in that the function is here larger than all the nearby points, but also global in the sense that this is the largest value this function achieves on the entire line. So again, this is a guess that we're going to verify rigorously that the derivative f prime should vanish at these sorts of local and global maxima or minima. Good, okay, I will plow on, but you should interrupt if you have thoughts. And I think one of the more interesting, I think we'll do this in a few more sessions, but I hinted before about this interpretation of the second derivative, and I gave you this idea that the second derivative is somehow measuring how different a function is from its average value at nearby points. So I think I hinted that, say, for a parabola that opens up, the function, well, the average of the function at nearby points minus its value in the middle is positive. So the second derivative is positive. F double prime is positive here. Similarly, if it's downward opening, then the average value minus the value at the middle will be negative. So the second derivative is negative. Here the second derivative is back to being positive. And the word that describes this geometrical feature is concavity. So we use the phrase concave up, or upward opening, if it has this property that the average value of the function minus its value in the middle over some interval is typically positive, and that means that the function opens upwards. Similarly, if the second derivative is negative, we call it concave down. The function opens downwards, like a negative opening parabola, minus ax squared for a positive. So this will be one of the later major applications of the derivative to understanding graphs of functions. But anyway, okay, so that's where we're going. That's I haven't actually told you anything real. These are just words. So if you are happy with that bird's eye view, I'll pause for a moment in case there are further suggestions or thoughts about any of these ideas. But if you are happy with these ideas, then we will start extremization.
I'm ready to go on.
Cool. Okay, so let's start with these finding maxima and minima, the way I suggested. So first we have to define precisely what we mean by a maximum if we're going to prove things about it. So let f be a real valued function. So it has this domain f, and we're going to consider a set of points A on the domain. So A is a subset of the domain. It doesn't have to be the whole domain. And the definition is that a point x in this set A is called a maximum point for f on A if the value of f at that particular point x, so remember x is the thing we're defining as the maximum point, so if f of x is greater than or equal to f of y for every other point y on A, right? So I've drawn an example. We should be very careful about several points of this definition. One, that the greater than or equal to, and two, that we have no guarantee that x is unique. The definition only says x is a maximum if f of x is greater than or equal to f of y for every other y in A. So for instance, if this interval here, where this curve is defined, if this is our interval A, there are actually many maximum points on A, because x1 is a maximum points, for instance, because x1 has the property that f of x1 is at least as big as every other f of y for every y on A. x2 is a maximum point. x3 is a maximum point. Actually, any point in this plateau here is also a maximum point. So we should be very careful about this definition. We're defining maximum point to just mean that this is the point that is greater than or equal to, its output is greater than or equal to every other output in the interval. So there can be many of them. There can be many maximum points. There will only be one maximum value. So maximum value means this thing, f of, say, x1 or whatever, which is the same as f of x2 and f of x3. So two definitions. Maximum point is the x value. Maximum value is the y value, where the maximum is achieved. And one more comment is that I'm going to give you many definitions involving maxima, and I'm not going to restate the corresponding modified definition for minima. I'm going to trust you that in your head you can simply replace the word maximum by minimum and replace this greater than or equal to by a less than or equal to, and understand that the same definition applies for minimum point. So in this case, x is a minimum point for f if f of x is less than or equal to f of y for every y, and then the number f of x is called a minimum value. But I'm not going to say that again. For every other definition, I'll just assume you are internalizing also the version for a minimum. Okay, good. Relatively basic, but thoughts on this?
Why do we say the set A is a subset of the domain of F and not subset back?
Oh, yeah, that's a good point. We could also... Actually, that's just me being sloppy. Good. I should say subset ek, because we will sometimes let A be the whole domain. Very good. You caught me. Good. Other corrections or thoughts?
I have no thoughts.
Excellent. Okay. All right, so this will be the first major result. So we're going to try to prove this thing about derivatives being 0 at these maxima. So here's the theorem. Let f be a function defined on an open interval. This will be important later. We're only going to prove this for open intervals. So it's defined on the open interval ab, and then we say x is a maximum or minimum point for f on that interval ab. So remember, whenever we say maximum point, we have to specify what is the set A. So this is a maximum or minimum on A. We also assume that f is differentiable at the point x. So I'm just flagging these two assumptions. One, that we're considering only an open interval, and two, that we're explicitly assuming f is differentiable at the maximum or minimum point. But if you make those assumptions, then here's the conclusion of the theorem. Then f prime of x equals 0. So again, I'm belaboring this point, but all we're proving, this isn't a very complete theorem, because we're just proving that if there's a maximum point and f is differentiable at the maximum on an open interval, then the derivative is 0. We'll have more work to do later to strengthen this result. And before starting the proof, I just want to give you a sketch of the idea of the proof we're going to use. So I'm going to prove just the case for a maximum. Again, I'll trust you to see how you could just reverse the proof to prove for a minimum. But if x is a maximum, we're going to, since we're trying to show the derivative has to be 0, all we're going to do is bound the derivative between positive and negative values. How do we do that? Well, we're interested in the derivative here at this point x, so we're just going to look at values of the secant line slopes which limit to the derivative. We're going to look at values of the secant line slopes from the left, which are all positive, because this guy's a maximum. Then we're going to look at slopes from the right, which will all be negative. So we're going to say that the tangent line in the middle has to be bounded between those positive and negative slopes. And the only way that you can have be bounded between these positive and negative slopes is if you're exactly 0. So it's almost like a squeeze theorem type proof, but I will make that much more explicit on the next slide. But before starting the proof, is the idea and the statement of the theorem clear?
Yes. Do we actually end up using the squeeze theorem?
No, we don't actually. Yeah, maybe I shouldn't have said that. We don't actually use the squeeze theorem, but it will be a
Okay.
similar argument.
It seemed like it was something that you actually might be able to do.
Yeah, I wonder if you could have an alternate proof of this that just explicitly uses the squeeze theorem. I don't know. I'll think on that. There might be a different way to prove it. I don't know. I just picked this kind of sloppy way because it's not, I don't know, it's not super hard, so you can just kind of brute force it. Okay. All right, here's the proof. So I've already kind of sketched the idea with the picture. So here's the x plus h. So what we're going to do is, again, look at secant line slopes from the left and right. So we'll let h be a number so that this sum x plus h is still within the interval ab. We have to be careful because we're only considering f defined on ab. So if that's true, then the output f of x must be greater than or equal to the output at this other point x plus h by definition, since f has a maximum at x. This is the definition again of maximum point. You have to be greater than or equal to the value at every other point. Okay, that's not bad. Let's just do algebra then. So I'll subtract f of x from both sides, take a minus f of x here, and that gives us f of x plus h minus f of x is less than or equal to 0. Now you can probably see where I'm going with this because this looks suspiciously like a difference quotient. So we're going to consider the case where h is positive and the case where h is negative separately. So first the case where h is positive. If h is positive, I can divide both sides by h, and it does not reverse the inequality. Right? You can divide inequalities by positive numbers without changing the direction. So when h is positive, you simply divide both sides by h. The right side is still 0, the left side looks suspiciously like a difference quotient, and now we can take a one-sided limit. Right? So I'm going to take a limit as h goes to 0 from above. Why above? Because this only works for values of h which are positive, greater than 0. So this is the first half of the proof. We've got this bound, that the limit as h goes to 0 from above of this thing, which is going to define the definition of the derivative at x in a moment, we've gotten this bound that the limit from above has to be less than or equal to 0. Okay, so now let's see the second piece when h is negative. So when h is negative, it's almost the same thing, but now when you divide by h, it reverses the sign of the inequality, right? So when I take this line, divide by h, I still have this difference quotient on the left side, but now the inequality switches from a less than equal to a greater than equal to, right? So that's conspicuously been done here. So this is dividing by h negative, right? Divided by h when h is less than 0. Okay, so now we can again take a one-sided limit. We have to take the limit as h goes to 0 from below, because this argument only works, this half of the argument only works when h is less than 0. But doing this gives us the second bound that the limit as h goes to 0 from below of this thing must be greater than or equal to 0. So that's good, because now we have two different bounds, right? We have a bound for a one-sided limit less than or equal to 0, and a bound for a one-sided limit which is greater than or equal to 0. Now this is where we use this assumption. We explicitly assumed that f is differentiable at x. And the definition of differentiable is that the limit, this limit, as h goes to 0 exists. So if the limit exists, that means that the two one-sided limits, the one-sided limits from above and below must be equal, right? If the limit as h goes to 0 from both sides exist, then it must agree on the left and the right. So if these two numbers are equal, the limit as h goes to 0 from below and above, if they're equal but one of them is greater than or equal to 0, and the other is less than or equal to 0, the only way this can be true is if that number which they are equal to, which is of course the derivative, if that number that they are equal to must be both less than or equal to 0 and greater than or equal to 0, which fairly obviously can only be true if that number is 0 itself. So that's the proof. Proven that under these conditions, if x is a maximum, then the derivative f prime of x must be 0. Good. Thoughts on the proof?
I have no thoughts. It is clear to me.
Good. Yeah, this one's not super bad. So, okay. Now we're going to dig in on those assumptions I flagged for you, this open interval and differentiability. So let's see what happens when we don't have those. So first, let's look at the function, the familiar parabola f of x equals x squared. So I'll just draw out this guy. And let's look at the intervals, say, -1 to 2. So from, I don't know, here to here or something. Okay, so I'll ask you, since this is a challenge, what is the maximum value, which you can kind of tell just by looking at the graph, what is the maximum value of f on this interval -1, 2 inclusive?
I believe that the maximum value is going to be 4.
Good, yeah, so maximum value on, I don't know how to write this, maximum -1 thing is 4. Okay, what's the derivative of f at that point where the maximum value is 4?
I believe it is also 4.
Yeah, because f prime, the x value is 2, so 2 times 2 is 4. Okay, so in particular it's not 0. Why is it not 0? I thought we just proved a theorem that whenever you have a maximum value, the derivative must be 0. Well, well, I'll ask you now that I've just made it very blunt, but which assumption have we violated?
That AB is a closed, that AB is an open interval.
Right, yeah, so the theorem explicitly assumed open interval. And now we see quite obviously why the thing fails for closed intervals, or sorry, yeah, why it fails for closed intervals, because you could just take any function which is like increasing and make a closed interval, and if the function's increasing, your maximum's always going to be at the right endpoint, right? Because this thing is just getting bigger and bigger. So this open interval assumption, I mean, is actually quite important for the conclusion that the derivative is 0 there. Okay, second example. So our favorite kinky function that has a kink at the origin, the absolute value of x, same interval, say -1 to 2. So now let's think about a minimum. What's the minimum value of f on this interval -1 to 2?
0.
Good, so minimum value is 0, and what is the derivative of the function at that point?
It is undefined.
Good, so f prime does not exist. Okay, so I thought we again proved a theorem that the derivative has to be 0 at the minimum, so why does that argument not work?
Because once again, we have supplied a closed interval rather than an open interval.
So that's actually not the reason. What? Let me just replace this by an open interval. So I've got the open interval. Is the minimum still at 0?
Yes.
Good, okay. So the closed interval wasn't the problem. Uh, what goes wrong with this argument? So if I apply the same thing to the open interval minus 1 to 2, why is the derivative undefined at the minimum?
Because it approaches different slope from each side, and that slope does not approach 0.
Yeah, so that's the reason why the derivative doesn't exist. But why does the theorem not apply here? Because the theorem tells me the derivative does exist and it equals 0. So why can we not apply the theorem to conclude that the value of the derivative must be 0 at this minimum?
Have we assumed that for the range AB that f of x is C1?
Yeah, we explicitly assumed it's differentiable. So let me go back to the statement of the theorem. Fuck, this thing. Yeah, so again, in the hypothesis of the theorem, we said x is a maximum and f is differentiable at x. So we actually didn't quite need a C1. C1 would mean it's differentiable everywhere in the interval. We didn't assume that. We just assumed that the derivative exists at the maximum point, or minimum. So actually the argument I gave you a moment ago about, well, why can't we apply the theorem? I thought the theorem tells us the derivative exists and it's equal to 0. That's not true. The theorem assumes the derivative exists at the minimum, and if the derivative exists, the theorem tells you it must be equal to 0. So clearly the theorem does not apply here if the derivative itself does not exist at the minimum. And it's fairly easy to see why this should be true in general. If you have any function that achieves a maximum somewhere, you could pretty easily break the theorem, because the theorem is supposed to tell you, the derivative here is 0. So you could pretty easily break the theorem by just changing this function a little bit to go to that point where it's a maximum and make it pointy there. Like just change the function a little bit so it now has like an absolute value type kink. And then that would break the theorem, right? Because you would say, now the derivative doesn't exist there because I put in a kink. So the point of this whole rigmarole is that the function we have, the theorem we have so far only works if the derivative is assumed a priori at the beginning to exist at the maximum or minimum. Okay, good. Kind of beating a dead horse, but it's important to understand the assumptions that go into these things. Good. Questions on this?
I have no questions.
Cool. I think these are what you told me a moment ago. Maximum value is at 4. Derivative is not 0. It's an endpoint of a closed interval, so it doesn't work. Same thing. Here the minimum was at 0, where that is the minimal value, but the derivative is undefined, so the theorem does not apply. Okay. Alright, so here's one where the theorem does apply. We have a function f, which is a parabola. We're going to find the minimum of this function on the interval from 0 to 3 in 2 ways, just to contrast how you do this in an algebra class. And then after doing it algebraically, I'm going to ask you very carefully to tell me what the theorem guarantees about this function, if anything, on this open interval. So, by the way, it's a polynomial, so we know it's differentiable everywhere, and we're assuming it's an open interval, so the theorem's totally fine. So first thing I'll ask you, if we're just going to try to guess the minimum by doing algebra, say by completing the square on this guy. Now, perhaps this will be embarrassing for both of us to try to recall algebra 2 knowledge, but what do I do to complete the square of this quadratic?
I don't know if complete different word for factor.
It's different. Yeah, factoring is writing it in the form x minus a times x minus b, so this is factor. Completing the square means to write it in the form x minus a squared plus b. So these are different.
Oh boy.
Whoops.
So I am inclined to believe that we can split that 4 into 3 plus 1.
Good. Okay, so let's do that. Plus 1, plus 3, and then what?
And we can factor the left bit to see that this is going to be... Oh, it's going to be x minus 1 squared.
Minus 1 squared plus 3. Good.
Yeah.
Okay, so can you
I was thinking pulling the 1 out, actually, and factoring... I don't know what I'm saying, yeah.
Oh, in this step you were going to pull a 1 out instead of a 3 or something?
Yeah, that actually worked better.
Yes, good. Remember the trick for completing the square is this minus b over 2a, right? This is that the thing? Or is it minus b over... Yeah, this is it, right? Because minus b over 2a would be 2 over 2 times 1, which is 1, and then this is the number which you want to add and subtract. So I think of it as you added a 1 here, and then you subtracted a 1 from the 4 to get a 3. So anyway, I won't belabor that point. Okay, so if you were writing a proof now that you have this factorized form, and you wanted to prove that this guy has a minimum at a particular point, what words would you say to argue for why this guy has a minimum at a particular point?
So I may have missed the point of the question, but could we find a point where x minus 1 squared equals 3?
Well, if we're trying to find the minimum, then the point where x minus 1 squared equals 3 is not that interesting, because 3 plus 3 is 6. And 6 will not be the minimum, right? This guy can get much smaller than 6.
I meant to say negative 3. Oh, wait.
Is there a real number which squares
Right.
to negative 3? Whoops.
All right. Attempt number 3. We're going to look for one where x minus 1 squared equals 1.
1. I think we can get better than that. So this is a sum of the square of a real number. So this thing is always greater than or equal to 0, right? So this thing is always greater than or equal to 3, right? So 3 is a lower bound for this quantity. So the best we could possibly do in finding a minimum, the best we could do for a low value of this sum is to get 3. Now, what value of x could we plug in that would achieve that lower bound of 3?
Plug in 1.
Yeah. So
I suggested the x minus 1 squared equals 1 because I saw that the c of the original equation was 4.
so you're pattern matching. You're just looking at numbers and doing numerology.
I thought, how do I word it? That the quote-unquote y-intercept is the lowest point, but that only applies to lacking a b-value.
Yeah, I think that's different. This guy's a parabola, so an upward opening parabola is always going to have its minimum at the vertex, right? So it's not the intercept necessarily, but it will be the place. Well, we could have gotten that, I guess, just by doing the negative e over 2a thing here as well. But this is nicer because now we have a proof for it. You could actually write an algebraic proof and just say, well, this thing is always upper bounded by 3, plugging in x equals 1 achieves this bound, and therefore x equals 1 is the minimum value. Okay, so that's the solution by pure algebra. Now, what does the preceding theorem specifically? And I'll ask you to word your sentence or your response carefully so that we know just what the theorem is guaranteeing us and not more. But what does the theorem we just proved tell us about this question of where the minimum is?
Is at the vertex.
Uh,
Prime equals 0.
The theorem certainly has something to do. Whoops. It has something to do with the statement that f prime equals 0, right? But does the theorem tell us that f prime of x equals 0, the point where this occurs, is the minimum?
Right.
Yeah, we should be very careful at the words we say. What you said is of course correct, but the statement of the theorem is that if x is a minimum, then f prime of x equals 0. So I'm just hammering the logic here. Logic is just the order of implication. The theorem assumes that a point is a minimum and then tells you that the derivative is 0. It does not go in the other direction. The theorem does not tell you that if the derivative is 0, then it's a maximum or minimum. That's the opposite order. That's the converse. So when I say explain carefully what the preceding theorem tells us, it doesn't tell us that f prime of x equals 0 implies x is a minimum, but it does tell us that if x is a minimum, it implies that f prime of x equals 0. Right, so as you say, we could just take the derivative and say this is fine, this is 2x minus 1, so, whoa, minus 2, what am I doing? And that equals 0 when x equals 1. But you should just say the sentence very carefully. By the preceding theorem, we know that if there exists a minimum on this open interval, it must occur at x equals 1. Right? That's what it tells us. We could actually go one step further if we don't just use the preceding theorem. If we were writing a proof, we could do this argument I just showed you, which tells us if there is any minimum on this interval whatsoever, if there's a minimum, then the derivative is 0 there, which means the point is x equals 1. Then we could combine that with a thing we proved in chapter 2, which is something called the extreme value theorem. Do you remember this extreme value theorem? Do you remember the statement of this theorem?
I remember what it is. I do not remember the statement.
Okay, the statement is if f is continuous on a closed interval AB, then f achieves, actually we prove both, f achieves its maximum and minimum on AB, right? We proved two things similar to this. We proved a boundedness theorem that showed that if f was continuous, it had an upper bound and a lower bound. Then we proved the extreme value theorem, which says that, oh, by the way, in addition, there's a point, say x, where f of x equals the maximum, and some other point, say y, where f of y equals the minimum. So if we wanted to be very careful about the proof here, we'd have to say by the extreme value theorem, we know that there is a minimum, a point where x achieves its minimum on this interval. And then by this theorem, a moment ago, because we know that there exists some minimum, then that minimum must be 1, x equals 1. So it's kind of a convoluted argument. I'm just highlighting how weak that theorem that we just proved is. It's really very shitty. It doesn't guarantee us anything that this is the minimum. It just says if there's a minimum, f prime is 0 there, which is not the order we want really. Okay, but I don't want to belabor that too much. Thoughts or questions on this?
I do not have any thoughts or questions.
Okay, so let's try to do better. Right, yeah, well, I'll just say these words again. This was completing the square. Non-negative term, lower bounded by 3, hits it at 1. The theorem tells you if there's a minimum, it occurs where the derivative is 0, so if there's a minimum, it's x equals 1. Great. All right. Okay, so this is a rehash of the words I just said. That theorem we just proved is a bit weak. It doesn't give us guarantees. It doesn't work for closed intervals. So we'd like to develop some more machinery to get a more powerful result. So first, I'm going to use some words in stating the more powerful result, so I will tell you what the words mean first. There's no math here. This is just learning definitions. So we've seen that we're interested in these places where the derivative is 0, right? They appeared in the previous theorem. So I'm just going to make a word for those. The word is critical point. So a critical point of a function f is a number x where f prime of x equals 0. Critical point just means place where the derivative is 0. The output of the function f of x at that point where the derivative is 0 is called the critical value. So not rocket science. Okay, one more thing. Since we're trying to fix the closed interval bullshit, if f on a closed interval AB, we want a word for those two endpoints of the interval, and we'll call those boundary points. So A and B are boundary points of f if it's defined on the interval AB closed. One more thing, so I hinted at this with the picture when I showed you, say, a local maximum, which is larger than all nearby points, but maybe not larger than points that are far away. So if f is a function and A is a subset of the domain, as you say, I really should have done this, subset EQ. A point x is said to be a local maximum for f on A if there exists some delta greater than 0 such that x is a maximum point. Remember, we already defined maximum point. If x is a maximum point for f on A intersected with that interval, x minus delta, x plus delta. So what does that mean? Well, it's just rigorizing the words I've been saying to you when I said local maximum, right? When I said local maximum, I just said it's larger than nearby points here. What do I mean by nearby points? That's not a very mathematically rigorous statement. By nearby points, I just mean you can find a delta and then make this interval, which is from x minus delta to x plus delta, open, and then this is a maximum point on that small interval, right? So this is what I mean by nearby points. Just pick a delta, it's a maximum on that interval. Well, the intersection of that interval with A. Okay, questions on those definitions?
I have no questions on the definitions.
Good. Okay, so first a very easy proof, which is actually a corollary of our previous theorem about this local maximum stuff. So if f is a local maximum, or again a local minimum for f on an open interval AB, and the derivative at x exists, so f prime of x exists, then again f prime of x equals 0. This is almost the same as the theorem we had several slides ago, but remember the theorem on the previous slides had a slightly different definition. There, this was replaced by a maximum point on A. So I'm just being very careful here. We have a new definition, so I'm just showing that the same result holds for this local notion. But the proof is very easy. You just use the definition of local max or local min, pick a delta, so that x is a max or min on this interval, x minus delta, x plus delta. And now we can apply the previous theorem. The previous theorem told you that if f is defined on this open interval and it's differentiable at x, and x is a local max or min, then f prime is 0. Well, we've got our open interval now by using the local max or min property. So now we just apply that theorem, and f prime is 0. So very easy proof. It's just the only step was converting this thing to an interval where it's not just a local max, it's an actual maximum point. Okay, questions on this?
I have no questions.
Cool. All right, so let's fix the closed interval thing. Here's the theorem. Well, all right, I'm getting tired of my own voice. Would you kindly read the theorem?
Alrighty. I just recently turned on push to talk, so this is fun. Actually, that makes it easier because then my mic won't cut out. Anyways, theorem: if x is a maximum or minimum for f on the closed interval AB, then one of the three things must be true. F prime of x equals 0, x equals A, or x equals B, or f of x f prime of x is not defined. Begin proof. Suppose x is a maximum or minimum, but is not a point of type 2 or 3. Then consider the function f on the open interval ab. Since f is differentiable at x, by our previous theorem we have that f prime of x equals 0. So we have proven that a maximum or minimum point, which is not type 2 or 3, must be of type 1, but this is logically equivalent to saying any maximum or minimum point must be of type 1, 2, or 3.
Good, okay. So note that these type 2 and type 3 cases are exactly, in the challenge a few slides ago, the kind of pathologies or the examples that we didn't like. Right? For instance, we considered the parabola on -1 to 2, and you told me that the maximum on that closed interval occurred at x equals 2. So that was a point of type 2, because that was one of the endpoints. That was the endpoint B. Then the second pathology, or bad thing, was the absolute value function. And again, you told me, well, the minimum is at x equals 0, but the theorem doesn't work there, because f prime is undefined. So this is often what you do in mathematics when you want a theorem to be true, but you find some examples where the theorem breaks, where it's false, and then you just modify your theorem and say, okay, well, let me just enumerate the things that could possibly happen. Either it works the way I want it to, or one of these possible things could break, and those are the only possibilities. Right? So the only content of this proof was to demonstrate that those are the only possibilities, and nothing else could go wrong. Right? But that's actually pretty easy, because if neither of these two things go wrong, so the max or min is not at an endpoint, and f prime of x is well defined, so it's not undefined. If these two things are false, then that means we can just drop the endpoints, replace the closed interval by an open interval, and then apply the previous theorem, because we know f prime of x exists. So yeah, it's not a lot of intellectual work going on here. We're just saying that if these two things don't break, the previous theorem applies, so f prime is 0, which is good. So these three possibilities are worth keeping in mind, because often calculus problems will ask you to find a max or min on a closed interval, and then you have to be careful. You have to say, okay, I have to find all points that are of one of these three types and check all of them to find where the true max and min are. I'll show you an example of that in a moment, but first, questions on the closed interval stuff?
I have no questions.
Good. All right, so let's actually solve a problem. So let's think about this function x cubed minus x, which I actually showed you a plot of way earlier in the bird's eye view. So we'll do this and then use our favorite closed interval from -1 to 2. So first I will ask you, enumerate all the points that are in those three classes. So the critical points where the derivative is 0, the boundary points, and any points where the derivative is undefined. So tell me all of those.
So working from back to front, we see that this is a polynomial, and therefore the derivative is defined for all on this closed interval.
Good. So there's no points of type 3, because it's defined everywhere. Good.
Our boundary point A is -1 and B is 2.
Good.
And here's where it gets fun. So, since, let me think. Both of these are two odd powers, so stuff gets more complicated.
Why is it more complicated? It's the same power rule regardless of whether it's even or odd.
Oh wait, could we divide by x?
That's not useful. I mean, if you
I
divide
mean,
by
factor out an x.
You could. I mean, you could factor out an x and write this as x times x squared minus 1 and use the product rule. But why wouldn't you just use the power rule directly on these guys?
What do you mean?
I mean, we're trying to write down the derivative, right? We're trying to find f prime of x and set it equal to 0. So what's the derivative of x cubed minus x?
X cubed minus x is going to be 3x squared minus 1.
Good. So we're trying to find points where that is 0, and what are the points where that happens?
Okay, add 1 to each side, then divide by 3, 1/3, square root of 1/3.
Plus or minus, but yeah.
Right.
Good. Okay. All right, so those are the points we have to consider. We have to look at 4 points. Minus 1, 2, plus 1 over root 3, and minus 1 over root 3. Okay, so I'll do the 2. We'll split the work. We have to. Wait, what are we doing here? We're trying to find the max and min. We know the max and min have to be at one of these 4 points, so we're just going to brute force it, compute f at all 4 of these points, and look for the biggest one and the smallest one. Right? Okay, so I'll do these 2 for you. So what is f of the positive 1 over root 3? Well, that's 1 over root 3 cubed minus 1 over root 3. Well, 1 over root 3 cubed is 1 over root 3 squared, which is a third, times 1 over root 3, right? So that's 1/3 times 1 over root 3 minus 1 over root 3. Why did I write it that way? Because if you factor out the 1 over root 3, this is 1 over root 3 times 1/3 minus 1, but 1/3 minus 1 is negative 2/3. So this is negative 2/3 times 1 over root 3. Good, so that's one of them. Actually, I lied because now I've gotten lazy, so I'll ask you to tell me what to write. When I compute the second root here, f of negative 1 over root 3, what should I write next?
And just following the form of what you've already done, we're going to have 1 over root 3 cubed minus 1.
Well, negative 1 over 3 cubed, right? Good, okay, what next?
And that is going to equal, we're going to keep the minus sign in front and have 1 over, well, let's see. Yeah, negative 1 over 3 times negative 1 over root 3. Or the negatives cancel out and we can...
Oh, there's only one negative, right? So negative cubed is
right.
negative, right? So don't forget to cube both. You cube the 1 over root 3, you cube the negative. Good, plus 1 over root 3. And then what does that simplify to?
I believe you're suggesting factoring out the 1 over root 3.
Yeah, so 1 over root 3 times minus a third plus 1. So what's this?
That is going to result in a thinking. Oh, 2 over root 3?
2 over 3 root 3, right?
Okay.
This thing in parentheses is 2/3. Minus 1/3 plus 1 is 2/3. 2/3 times 1 over root 3. Good.
Okay.
Good, okay, these two. Now the easier ones. So what is f of minus 1?
0.
Good. What's f of 2?
That will be 6.
Good, okay. Alright, so we have these 4. Now I will ask you, what are the max and min on this closed interval?
I believe that the minimum is minimum value is going to be f of 1 over root 3.
Good, so this is the minimum value, and the max value
is f of 2.
Good, okay. Max value. Okay, so now we have extremized this function. We have found its max and min on this interval. And I'm going to jump to the answer analysis to see whether this makes sense before going back. This is the same plot I showed you before, so let's see if this makes sense. I've showed you a little more than the interval in question, but we see that if we're going from minus 1 here to 2, which is over here, a little past the plot actually, then visually it makes sense that at 1 over root 3 we're at the bottom of this valley, so indeed that's the minimum value on this interval. And then now we see why the endpoint was the correct maximum value, which was at x equals 2, because far to the right this guy just is strictly increasing everywhere. So he gets bigger and bigger So the max value just pushes you to the right endpoint. Good, so answer makes sense, and then this is just rewriting the algebra. So we got the critical points, as you told me, solved that, listed the boundary points, no points where f prime is undefined, did some arithmetic to get these, typo here, this one's the negative 2/3, whoops, positive 2/3, and that was the max and min then. Good, so I'll put our algebra back up. Good, okay. Questions on this procedure?
I have no questions.
Okay, I find these functions, so these sorts of problems kind of fun. These maximization problems, they're like crunchy. It makes you feel powerful the first few times you do them, to find these maxima that you couldn't have done before, because you know, before learning this, you probably only know how to find max and mins for parabolas, right? So it's kind of fun when you realize you can now do this for any polynomial if you have enough patience. But I'm not going to do more examples of those today, although there'll be plenty of daily challenges where you can do more of those. Instead, we will jump to the mean value theorem stuff. But before I do that, any big picture questions about the extremization stuff?
I still have no questions.
Okay. I like to keep checking. Sometimes, fuck. Okay, go away, keyboard. There we go. I feel like
What happened?
I don't know what happened there. I think I might have clicked a pen button by accident. It was weird. Okay, so we did maxima, or we started at least maxima and minima. One of the other things in the bird's eye view I suggested was that we would like to be able to tell whether a function is strictly increasing or strictly decreasing on some interval, and we suspect that that should be related to the sign of the derivative, where it's positive if the function is strictly increasing and negative if it's strictly decreasing. So probably next time, I guess Saturday, or no, Friday maybe, unless you have other shit, we can do more details on that. But although it's a pretty clear geometric statement that this just should be true, actually proving it carefully that this thing is strictly increasing in the way we defined it in chapter 1 is trickier than you would expect, actually. So we'll need some intermediate results. And as it turns out, the intermediate results will be very powerful in their own right. So it's worth laying the groundwork to do those and kind of just thinking about these theorems. So today we'll do the mean value theorem. It's the last thing for today. And as I've alluded to kind of, that this MVT is another very overpowered theorem. It can give you surprisingly strong results, similar to the intermediate value theorem, which is also kind of overpowered because it's kind of a topological idea. But before proving the mean value theorem, we're going to prove a weaker version, a special case of the mean value theorem, which is called Raleigh's theorem. So this is Raleigh's theorem. The statement is that if, now notice that we make different assumptions about continuity and differentiability. If f is continuous on the closed interval from a to b, and differentiable on the open interval from a to b, and the values at the two endpoints are equal, f of a equals f of b. So I've drawn an example here, right? So this is supposed to be continuous and differentiable, and the f of a and f of b endpoint values are the same. That's the setup. If that's true, Raleigh's theorem tells us the conclusion is that there must be a number x in the open interval from a to b with the property that f prime of x equals 0. There must be a place where the derivative is 0. So the idea is basically if you start when at x equals a, if you start at f of a and then you evaluate for a little while and then end at some place b with an f of b, and if you end up at the same place where you started, that means f of a equals f of b, then you had to turn around somewhere, right? If you started going up, somewhere you had to turn around to come back down, and that's where the derivative is 0. Or if you started going down and then eventually had to come back up, you had to turn around somewhere and the derivative is 0 there. Or of course the other option is that you didn't move at all, you just stayed constant on that interval, but if you stayed constant, the derivative is 0 everywhere, so we very easily can find a point where f prime is 0. That's the idea, but I will prove this on the next slide. First, questions about the statement.
Actually, I thought. Because of you saying the phrase, if you end up where you started, you had to turn around somewhere, I'm now thinking of one of the things that happened in Curse of Strahd.
Please tell me what vampire-related thing is reminded or has to do with that sentence.
Basically, there is a slow fog following us in game, and our Warforged thing decides to turn around and walk into it with a rope tied to it, and it walks out about 40 feet. Doesn't turn around, but it does come out of the fog the same way it went in.
Yeah, that's like the shitty plot device to keep you from ever leaving the weird Strahd demiplane, right? You can't leave because if you walk into the fog, it just spits you back out, right?
Right.
I did enjoy that. Although if I remember correctly, those gypsy fuckers. I don't know if you met them yet. The gypsy fuckers can go through the fog or something, but I don't know.
This sounds fun.
Yeah, maybe you haven't met the gypsies yet. I apologize if that's a spoiler, but I think the gypsy fuckers are one of the most interesting character groups in Curse of Strahd. But
I have not met them.
oh, you should. Okay, question for you. This is really just a question about how we state theorems. Why wouldn't we just have said the state? Why wouldn't we have? Let me say this differently. The assumptions we made here are that f is continuous on the closed interval a to b and differentiable on the open interval a to b. Why would we not make the assumption, why not assume that f is differentiable on the closed interval a to b and not say anything about continuity, because if we had stated the assumption this way, so that f is differentiable on a to b, then since differentiable implies continuous, then f would automatically be continuous on the closed interval a to b, so we wouldn't need to say anything about continuity. So it seems like it's verbose, where it seems like we're saying a lot more words than necessary to say it's continuous on this thing and differentiable on this thing. Why wouldn't we just say it's differentiable on the closed interval a to b to shorten the statement of the proof?
I guess we would like to ignore the possibility that x equals a or b.
Let's see, that x.
I don't know.
Oh, that the maximum, this thing could be a or b, or the point where it's 0, you mean? Yeah, I don't know if we're trying to ignore that case necessarily.
Yeah, I didn't quite word that.
Because well, I don't know. Yeah, I think the better reason why we say it this way is that the statement of the theorem as written is a weaker assumption. By weaker assumption, I mean we've assumed less here. This is less. My pen's. This assumption is weaker. So in math, if changing the assumptions in a way that makes you assume more, if you do that, it's said to be strengthening the assumptions. So this thing over here, the alternate way that I've written it, is a stronger assumption. Stronger, it just means the stronger one implies the weaker one. So if this thing on the right is true, then this thing on the left is true. That's what stronger means. The stronger one implies the weaker one. So the reason we phrased it this way is that when you state a theorem, you always want to make the weakest assumptions possible, because the less you assume, the more cases there are that you can apply the theorem, right? So you want to assume less, because then your theorem applies more generally. So this case here, why is this weaker? Because in this case we have not assumed that it's differentiable at the endpoint. So we don't want to assume that f is necessarily differentiable at these two endpoints. It could be part of a function that, I don't know, looks like an absolute value outside this interval, so it has kinks. In this case, the theorem wouldn't apply if we made the assumptions on the right, because here you would need to assume it's differentiable at the endpoints, which wouldn't be true. But the theorem does apply if we use the formulation on the left, where we don't assume differentiability at the endpoints. So anyway, this is just a kind of mathematician's style comment that you always want the weakest assumptions and the strongest conclusions that you can get.
Is it generally true that weaker assumptions imply stronger conclusions?
No. So, I mean, since a stronger assumption will always imply at least the same conclusions as the weaker assumption, it usually goes the other way. Usually weaker assumptions are weaker conclusions. But if you can do more work, if you're more clever in the proof and can get stronger conclusions without assuming more, right, then that's better. It's somehow like it's almost like you're in a fight and the assumptions are the handicap and the conclusions are the enemy you can beat. So it's more impressive if you can beat a grizzly bear with your arms tied behind your back, that is, get strong conclusions with weak assumptions. That's more impressive than if you can kill the grizzly bear with a gun, right? I mean, it's not true that the guy with the hands tied behind his back is necessarily going to be able to kill something bigger, but if he can do it with the hands tied behind his back, it's just better. It's more impressive. Good.
I have further question.
All right, let's do the proof then. So there's an embedded challenge for you in the proof. But the first statement, well, since we discussed this a lot, reminding you we assumed f is continuous on the closed interval a to b. So the first line of the proof says, since we've assumed f is continuous on the closed interval a to b, we necessarily know that f achieves its maximum and minimum value on that interval a to b. So my challenge to you is, why do we know that this is true?
I feel like this is the strengthened form of the minimum/maximum value that we did like 5 seconds ago.
So that was the one
Amazing.
Sorry?
Amazing response, I said. Sarcasm.
Yeah, so you were talking about the result about the derivatives, but that result tells you that if a point is a max or min, it must be of one of 3 types, right? A critical point, a boundary point, or a derivative undefined. So that's a different statement from this. That statement tells you if x is a max or min, it falls into one of 3 classes. This statement is saying f is continuous, and therefore it does have its max and min values. It's not saying anything about 3 classes of points. So this was a different result. What result do we use to guarantee this is true?
It says this has to do with the extreme value theorem.
Yes, this is precisely the statement of the extreme value theorem. Right. Why is that? I'll write the statement again in abbreviated form. F continuous on AB. Those are the assumptions. Applies that there exists x, y. So f of x is a maximum, so f of x is the max, f of z for all z, and f of y is less than or equal to f of z for all z. This is the extreme value theorem. So in particular, for the extreme value theorem proof, we needed continuity on a closed interval, so that's why we've assumed continuity on a closed interval. So I'm just explaining why we picked the specific assumptions we did, right? Because we wanted to use the extreme value theorem. Okay, so that's the first paragraph. Next, so now we use the thing you said a moment ago for the statement that maxes or mins must be one of 3 types, right? So we've assumed differentiable on the open interval a to b. So that rules out type 3 immediately. Type 3 is places where the derivative is not defined, or where f is not differentiable. So it can't be type 3. The only 2 remaining possibilities are that the max and min could be at a critical point or at an endpoint. Now it's worth backing up and remembering what we're trying to prove here. We're trying to prove there's a place where the derivative is 0, right? That's all we want. So if the max occurs at a critical point, then we're done. We got what we want, right? Because we're trying to find a place where the derivative is 0, and that's the definition of a critical point. So if either the max or the min, in principle they're different, if the max or the min occurs at a critical point, then just use that point to guarantee that's the place where f prime is 0, and then you're done. So the only case we have to handle is if neither of those is a critical point, if the max and min are both endpoints. So that's paragraph 3. We handle that case. So if neither the max nor the min occurs at a critical point, they both occur at these boundary points, which are the closed interval, a to b. But that case is actually pretty simple, because if the max and the min both occur at a boundary point, and we've assumed f of a equals f of b, so the two boundary value outputs are the same, that means that the max is equal to the min, right? If the max and min both occur at the same value, then the max and min are the same number. And the only way the max and min can be the same number is if f is a constant. It takes the same value everywhere. And in that case, if f is a constant, we've proven the derivative of a constant is 0. So in that case, we get what we want as well, since, again, we're trying to prove that there's a place where the derivative is 0. So if it's constant, just pick any point. That's the proof. Thoughts on Raleigh's theorem?
I do not have any thoughts or questions.
Sweet. Okay. I will ask a challenge for you then. So here's another incorrect argument. So, there's a typo. Absolute value of x. So I'm going to use absolute value of x again and ask you what goes wrong with this argument. So let f of x be absolute value of f. F is continuous on the closed interval -1 to 1, and it's differentiable, I claim as well. So if f is continuous here, and it satisfies the hypothesis of Raleigh's theorem that f of -1 equals f of 1, then by Raleigh's theorem, if I end up where I started, then somewhere I had to turn around. So there's a place where the derivative is 0. So I claim there exists a point between -1 and 1 where the derivative of f equals 0. And actually that's not true. So what's wrong with this argument, and what hypothesis did I violate? Which sentence in the previous paragraph I just spoke at you was actually false?
I believe that the usage of x in the closed interval -1, 1
Good. Okay, so
that affects the result.
Okay, so let's change it then. So what if I change the claim now? I say, all right, now I claim there's just a point in the open interval, -1 to 1, where the derivative is 0. Now, is that true?
Of course, it would be cheating if you let me look back at Raleigh's theorem, correct?
That's fine. I'll go back to the statement. So here's the statement of Raleigh's theorem.
I do not see anything wrong.
Okay, so it's certainly true that the absolute value is continuous on AB. Is the absolute value function differentiable on AB?
I wasn't sure if what you I thought you added on that it was differentiable there.
I did. I said that, but the thing I said was false. I said it's also differentiable, I claim. Why is that claim not true? Why is that a lie?
Steps breaking, as the absolute value function is not derivable where x equals 0.
Yeah, good. So, as you said, the tangent line approaches different values from the left and right, so it's not differentiable here. So, the point of this example is that even though Raleigh's theorem assumes differentiability on this entire interval, we actually do need that entire interval. If differentiability fails at even a single point, then Raleigh's theorem breaks, right? Because you might think, well, this function is mostly differentiable, it just fails at a single point. But no, when you assume a function is differentiable on an interval, that means every single point on the interval, and generically your claim will break if it fails at a single point. Okay, good. I apologize for injecting the lie, but I wanted you to hold my feet to the fire about the incorrect statement. It is indeed not differentiable at 0. Other comments?
I do not have any comment.
Okay, so the only slightly hard proof for today, good, here's the solution. Hypothesis says continuous and then differentiable, and it fails to be differentiable at 0, so it's not differentiable on the interval. Good. Alright, so this is, I think, the most important theorem probably in this chapter. Yeah, probably, actually. So this is called the mean value theorem. Here's the statement. So same hypothesis. This is why I'm belaboring these assumptions. Let f be continuous on the closed interval a to b, differentiable on the open interval a to b, the weakest assumptions possible. Then the conclusion is that there's some number x in the interval where the derivative of the function at that point, which is to say the tangent line slope, is equal to, now this is not a derivative, this thing on the right side is just the ordinary secant line slope between the two endpoints, right? A and B are the two endpoints. So this is the secant line slope. This is literally just the slope of the line you get by connecting the 2 points on the curve at those endpoints. So I've drawn that a little more clearly below. So here's a function y equals f of x in blue. The secant line slope is the slope you would get by connecting a comma f of a, that point, here's f of a, with b comma f of b, here's f of b, and you just draw a secant line between those 2 points. This theorem is telling you that whatever that slope is, whatever the slope of the secant line is, there must exist some point in the interval whose tangent line slope, the derivative, f prime, at that point, which is here called c in the graph, but there's some point c in between where the tangent line slope equals the secant line slope. Right, okay. So hopefully you see the parallel is very similar with the intermediate value theorem, because the intermediate value theorem was telling us something related but not about derivatives. The intermediate value theorem was telling us that if f is continuous and we have, two endpoints A and B, and then you pick some A, B, f of A, and then we pick, say, some y in between. The intermediate value theorem said you could always find a point where the value of the function gives you that point y. This thing is giving us something slightly different. This thing is saying you could always find a point in between where the value of the derivative matches some prescribed value, which is here the secant line slope. So they're closely related, actually. But good. So is the statement of the theorem clear?
Yes.
Okay. Let's do the proof. This requires a slight trick. You've seen this trick before, though. When we did the intermediate value theorem, you saw we often did this trick where if you want to show that something equals something else somewhere, it's usually easier to just subtract one of these from both sides and then show that that thing is 0. So if I subtract something from both sides and show there's a place where that subtraction is 0, then that's the same as showing there's a place where they're equal. This happens over and over in mathematics. Rather than showing things are equal, it's easier to subtract and show that that difference is 0 somewhere. So let's do that. I'm going to define a new function, which is literally just typo, f of x, f prime of x. That should be f prime. So I literally just subtracted this thing from both sides, except for the small subtlety that I had to multiply by x minus a. And I'll explain why I did that in a moment. So h of x is f prime of x minus this secant line slope, f of b minus f of a over b minus a, all times x minus a. Okay, so I'll ask you to justify this step first, and then I'll explain this factor. So I say clearly. Clearly is usually a signal that, I'm being lazy and don't want to explain why this is true. So why is h continuous on the closed interval and differentiable on the open interval? Oh, wait a sec. No, I lied. This was not a typo. That's supposed to be f, not f prime. Good. Sorry. I misled you. This is actually supposed to be f. When we differentiate, it's supposed to be f prime. Never mind. Ignore what I said before. This is correct. But question still stands. So why is h continuous on AB and differentiable on open AB?
So I'm just observing here. I don't know if it's any quality response, but it seems that when x equals a, we have that the entire right side is multiplied by 0. And so h of x equals f of x.
Yeah, good.
And have we defined f of x to be continuous on AB?
Yes, so that was in the assumptions of the theorem. So f is continuous on AB and differentiable on open AB.
And relatedly, let's see. So I'm thinking about what occurs at x equals b.
Good, so let's write that out. HB is f of b minus f of b minus f of a. Interesting. So now
I see now.
you see the trick. I multiplied by this because when we plug in x equals b, we get this nice cancellation, and then what's this thing equal to?
Let's see. That is simply going to be equal to negative f of a.
Two negatives, right?
Which a?
So positive f of a, yeah.
Right.
Because f of b minus f of b cancels, minus minus f of a is f of a. Good, so now you see why I cooked this factor up. Yeah.
Why isn't the f of a negative? Need clarification there.
So this is in the numerator f of b minus f of a, and by algebra minus x minus y is minus x plus y, right?
Okay, that makes more sense.
Let's just, yeah, distribute the minus sign. Good, so I distribute this minus sign on f of b, which kills the f of b, distribute the minus sign to the minus f of a, which is plus f of a. Good.
All right, understood.
Okay, so that was the next thing I was going to ask you, in fact, is to do the algebra to show that h of a and h of b are equal, and they're both f of a. Right, so now you see, again, why I cooked up this factor, because we're slowly trying to get this in a form where we can apply Raleigh's theorem. And Raleigh's theorem requires the function to be the same at the two endpoints. So you have to end where you started. So you cook up this thing so that the function ends where it started, which means that h of a is the same as h of b. Good, so that's one thing we need for Raleigh's theorem. The other thing we need for Raleigh's theorem is that h is continuous on AB and differentiable on the open interval AB. So we've assumed that's true for f. F satisfies these two assumptions, continuous and differentiable. How do we know that h, which is a sum of f and some other junk, how do we know that this sum or difference also has those properties?
Could you state the question again?
So how do we know that this new function h, which is f plus this other function minus junk, how do we know that this function h is continuous on AB and differentiable on AB? Maybe we should start by thinking about the function we add to f. So what type of function, what class of functions does this this object fall into? I mean, this whole thing's a constant, right? And then what's this?
I believe that is a linear function.
Yeah, so this is just some constant times a linear function, which is, just, again, a line or a polynomial, if you prefer. So how do we know that if f is differentiable, for instance, let's do the differentiability. So if f is differentiable, how do we know that adding f to a polynomial is still differentiable?
I believe the same way we prove, except the opposite. Well, we have used except the opposite way around, that the sum of, well, the derivative of a sum is the sum of the derivatives.
Yeah, true. So we've proven
Drivable, the entire thing is.
yeah, that's that result guarantees us that if you add a function which is differentiable somewhere to a function which is differentiable everywhere, since the derivative of the sum is the sum of the derivatives, that this new function h is also differentiable. And similarly, we also proved for continuity that the limit of a sum is the sum of the limits if they both exist, and we know that h is assumed continuous. This guy's a polynomial, so he's continuous everywhere. So indeed, the new function h is also continuous on AB. Good, good. So yeah, it's not an involved argument, but yeah, to just justify that the new function satisfies the assumptions. Okay, so h does that. H has the required property that it hits the same value at the two endpoints. Then we just blindly apply Raleigh's theorem. So by Raleigh's theorem, we're guaranteed that there is some point x in the open interval a to b where h prime is 0, right? Because remember, Raleigh's theorem tells you if you come back and h of b is the same as h of a, and you satisfy all those nice things, then there's a place where the derivative is 0. So we know that. We know there's a place where the derivative is 0. But if we just, directly from this top line, if we just differentiate h, well, apply linearity again, derivative of the first term, f, is f prime. Derivative of this thing, this is just a line. The line has slope minus f of b minus f of a over b minus a, right? Because this guy multiplies the x. So differentiate that thing, and if there exists a point where this thing equals 0, then clearly by adding this junk to both sides, at this point x, which we are guaranteed exists, we have that f prime of x equals f of b minus f of a over b minus a. And this is what we wanted to prove, that there's a point where the tangent line slope equals the secant line slope. Good, cute proof. Powerful result, though. Good, more thoughts on this?
I do not have any thoughts.
All right, then a challenge for you, which I'll ask you to kind of work through. This one might require some exploration or a couple steps, so feel free to say whatever comes to mind. But the statement is that we're going to assume this function f is again defined on this interval, closed interval a to b, and I tell you the derivative is 0 everywhere. So f prime of x equals 0 for every single input x in that closed interval a to b. And we're asked to prove that f is a constant function. So kind of intuitively this makes sense. I mean, if the tangent line slope is always 0, it's hard to imagine how this guy could not be constant. It seems like if he changed values anywhere, the derivative would have to be non-zero. But that's not a proof. In fact, to prove it, I claim we should apply that theorem we just proved a moment ago, the mean value theorem. So, well, to remind you, I'll just go back and show you the statement of that. Mean value theorem tells us that under these conditions, there's a point x in the interval where f prime equals this the secant line slope, f of b minus f of a over b minus a. So I'll, I guess, ask you, let's just apply the mean value theorem to this function f and follow our noses and see what it gives us. So I'll ask you, what do we get if, I don't know, let's just pick two random points, not necessarily the endpoints. So pick 2 points c and d, points in the interval, and I'll ask you, what do we get by applying the mean value theorem to, let's see, f. Well, let's just write it first. Let's not worry about this. Well, for mean value theorem applied.
I walk upstairs quickly.
Yeah, sure.
All right, and I'm in a quiet place again.
Ah, you exist. Okay, good to start.
I'm ready.
Okay, so I shall ask you. Yeah, so let's just pick 2 points. We're trying to prove f is constant, so let's just pick 2 points and see if we could prove that f has the same outputs at these 2 points. So pick 2 points C and D, and now I've asked you, what do we get if we apply the mean value theorem we just proved to the function f on, the interval C comma D? What should I write?
It would seem by the mean value theorem going straight from definition that we have that thinking. I believe that this is still applied to now. We have that f prime of x is going to be equal to f of d minus f of c over d minus c, I believe it is.
Okay, so yeah, MBT tells us that for some value of x, right? The theorem guarantees us there exists a point where this is true, right? Okay. Now what should we do? What can we use to extract more information from this statement?
I believe we see that f of d minus f of c over d minus c equals 0.
Good.
By, oh, well, by, what's the name? You know what I'm trying to say.
You mean by the assumption?
Yeah.
Good. Okay. Yeah. So we've assumed that f prime is 0 everywhere, and you've told me that f prime is equal to this thing at some value of x, but it doesn't matter what value of x it is because it's 0 everywhere. Good. So you say 0 equals f of d minus f of c over d minus c, and now what can we conclude?
Or by multiplying each side by d minus c, we see that f of d minus f of c equals 0.
Good.
Or d minus, or f of d equals f of c. You could just keep going on.
Yeah. So the mean value theorem applied on this interval tells us that f of d equals f of c. But at the beginning of the day, we assumed that C and D were any old points in the interval AB. They were completely arbitrary. So we started with picking any 2 points and then proved that the outputs of the function are the same at those 2 points. And that implies that the function must be constant, because that means that the function's values agree at every pair of points in the interval. So that's the proof. We've concluded that f is a constant function. Perhaps written somewhat more neatly, repeating the thing we said a moment ago, pick any points, say c less than d, so I could write the interval with c coming first. And as you say, by the mean value theorem, there exists some x where this equation holds. F prime is the secant line slope. And indeed, f prime by assumption, f prime equals 0 everywhere. So 0 is this side, which means f of d equals f of c. So f must be a constant function. Good. Powerful results. Overpowered theorem, I think. But alrighty. Parting thoughts or comments on the mean value theorem things?
I do not have any questions or comments about this.
Cool beans. Okay, so Friday still? Is that the next meeting, or do you have things?
I still do not know if the football game this Friday is home or not.
Okay. So
Figure that out.
should we just pick a different day rather than Fridays? Because I don't want to have to reschedule every other week. I just want to pick 2 days, and then we just settle down, and no one schedules other stuff those days. So would you prefer a different day, like Monday or something?
Would Monday and Thursday work?
Yeah, that's fine for me.
All right. That seems like it's spaced well, and works for my new schedule, as my schedule keeps getting filled in.
Yeah, you're very active. Lots of shit to do. Okay, Mondays, Thursdays, and then CD3 stuff done by Friday. All right. Sounds
Yes.
good.
Will you be able to get